Hello, everybody. Hopefully tonight finds you well, or today, tomorrow, or whenever you actually end up watching this. So, I'm. We had some snow here this morning. I haven't had to leave, so I've got a little bit in my driveway. I'll probably have to clean it out tomorrow morning, maybe. But so that's the advantage of working from home. You don't necessarily have to go out and deal with it. All right, so today I'm going to talk about a little bit about embedded systems. The chapter itself is a little thin, but that's okay. We'll cover it today and we'll finish it tomorrow, and maybe jump in and do a little bit of Maria at the end. I don't know. We'll see. Maybe I won't. We still have that reverse Polish notation decoder, right, where it comes in reverse Polish notation, and we need to decode it into regular infix. But we'll get back to that one. So, what is an embedded system? Oh, I should probably bring up my OneNote. Jeez, I feel like I'm losing my whatever touch I once had. That's all right. Here, we'll call this one Lecture 30. Just as a thought. That sounds reasonable to me. Okay. All right, now let's look at make sure everything's working. Okay. So let's look at what's an embedded system. Embedded system. We use them all the time, including you, right? Everyone does. When you drive a car, there are embedded systems in that car. So let me give you an example of that. Well, there are tire pressure sensors. So in the car, that doesn't right, because we have the system that tells you what the pressure is for those gauges, and that's that would be an embedded system. Let me do something that's a little bit less. The problem is in a car it gets really crazy. There's a lot of different parts that make it up. A smart thermostat. Not even a smart one, just a normal thermostat that has an embedded system in it. So I'll just use the one that I have. Mine's fairly simple. It's not that crazy. It is a digital one. And what it does is you can set the temperature for which your furnace will kick on, and you can set the temperature with which your air conditioner will turn on. So it's very, very simple in that indeed. But because it's programmable by the user, right, it needs to be able to change. And I can set it for whatever temperature I want for the heat. So that's like the minimum temperature before the furnace turns on. And so that's the temperature it will stay at. It will try to keep it at that temperature on the heating side of things, and on the cooling side of things, it tries to keep it at that temperature. Now, the interesting thing is because things will fluctuate a little bit, you have to have at least 3 degrees between them, because otherwise your furnace would turn on, then your air conditioner would turn on, then your furnace would turn on, and then your right, if they were the same number, you'd run into that risk. Okay, so an embedded system is any system that is it's a digital system. It's in or on something, anything, right? And I mean, oh, actually, let me think. Here we go. There's one. Wait, this doesn't have an embedded system, probably. So I have a fidget spinner that I got at DigiKey when I was up there a few years ago. So the interesting thing is here, it's got different patterns on these, and each one is the same, and then you can spin it, of course, and it has different effects, right? If you do that one, then you spin it, and then you do that one, and then you spin it. And it's just different. Fidget spinner, that's such an old thing. It's, you know, years ago, right? What, 5-6 years ago? I like playing with mine. Still helps me relax, right? So, I used to joke, and this is probably still some truth to it, that one of the best stress relievers that I had, this is years ago, was to fire up a game of StarCraft. This is back in the days of StarCraft 2, not StarCraft 3, but it would probably still apply in 3, and build a base of a whole bunch of Zerglings, and just charge around the map killing stuff. And you don't even care if you lose. It doesn't matter. You're just killing a bunch of Zerglings. Because your own guys die as fast as the bad guys do. So, and it's really not true, but it's kind of fun. All right, and it's virtual, so nothing's really getting hurt. That's interesting. So, oh, yep. Oh, right. Yeah. If you ever use, well, there's an example would be a coffee maker, the K-Cup coffee makers. Right? So those are embedded systems. It's got an embedded system in it. It's not terribly sophisticated, right? You push down the button, it drips some water through the cup, it punctures, right? But that's mechanical, the puncturing, and then it drips into your cup. Well, that's actually not completely true either, is it? Because if you don't put a cup in there, it won't go into your cup. So it just comes out a certain spout. And whatever's there to catch it catches it. And it could be nothing. We just try to be as precise in our speech as we can be. Okay, so the history of embedded systems is interesting. What happens is, remember when we talked about Moore's Law back a long time ago, right? Things get faster, or we can put more transistors per inch of silicon every 18 months or 2 years, depending on which version of it you're going to use. I think for this class we used 2 years, and that's probably the most prevalent one. It wasn't that long ago, and it was 18 months. But, so 2 years. Well, that means we can put more chips on a circuit, which means that the thing that used to be this big, which is about a foot, we can shrink down to less than, that's 6 inches in 2 years. And then 3 inches in 4 years. And in a decade, it's less than an inch. And in 2 decades, it becomes so small you can barely see it. Something that was 1 foot square is now, 20 years later, is now so small you can't even fit it on the head of a pencil, potentially. Maybe 10 times small. Well, that's 1,000 times smaller total, right? So yeah. Yeah, because each one is 2 to the 10th. Yeah. So what happens is, this is pretty cool actually. They used old technology on new circuits. And you'd think, well, how does that work? What they did was they already had developed. So it's actually quite expensive to develop a system, to develop a chip. And so what they would do is they would take, in 2000, they can go back and take the 1980s style of chip and the design for that, and they can make it on a chip that's small enough to fit on the head of a needle. Or something like that, or the scale. It's a light, tiny little speck. And what used to be big. So, and they already had it. The system already existed. It's already been designed. So they can just use it. And they've got 20 years of people using it. So that was one way to kind of do some embedded system work. The problem is, with that, and those are called off the shelf. So that would be off the shelf. The problem with that is it's going to have a lot of functionality that you don't need, right? Because if you take a system, an actual full computer system that has the ability to say, have a keyboard, right? And you're going to use this in a toaster. You don't need a keyboard, right? You don't need the ability to interact with the keyboard. So there's that part of the chipset that's in there that's dealing with the keyboard. You don't need it. You could throw it away. So it's just wasted. However, just for price, it's not wasted. Potentially, and it depends on, how these things can be manufactured. But once the machine is bought and paid for at some point, and then it starts creating these chips. Well, that machine might last for 10 years or 20 years. Well, it's creating these, right, that would be creating the old style chips. But then so these embedded chips, because they don't really change much as far as how much better they need to be. Like a personal computer, right? You want it to be better and faster and gooder, right? But a toaster, yeah, you want it to be better, but you don't need the chip in there to be that much better. Or a coffee pot, right? It just needs to be able to be fast enough so that you don't notice how long it takes to compute. And some very old systems can do that. Now, I'm not suggesting that we should take the 1980s computers, or at this point 2000 computers, to 2000, the year 2000. We wouldn't take those computers and put those in our coffee pots and toasters. Oh, maybe we would. I don't know. Well, we don't need to. This is also why, right, cell phones have gotten so much better over the years, and why they'll continue to get better. Although I heard something recently that at Apple, just at Apple, not at any place else, at Apple, since it's a interesting story. So let me to kind of go off on a tangent for a second. So, and it kind of is applicable a little bit, but at Apple, Steve Jobs was one of the founders of the co-founders of the company with Steve Wozniak. They were sometimes referred to as the two Steves. Well, Steve Jobs was the visionary. He's the one that came up with the ideas of what to do, and Steve Wozniak was the implementer, and he was more of the computer scientist, and he's still alive today. Actually, he's an interesting fellow. Well, I think I might have talked about him before, but he once dated Kathy Griffith. I don't know if you've heard of her. She's an older actress. She's probably about 50 or so. But she used to be around quite a bit, and she's done some things lately as well. And I think she's fairly active on Twitter. Not that is that unusual. Any case, um, they continued to come up with innovative solutions and innovative products when Steve Jobs was there. But Steve Jobs got fired from his own company. He got bought out and fired. It was kind of a big deal. Well, then the company stagnated, and their computers didn't get that much better. They got incrementally better, but it wasn't. It was small. It was not that much of a difference. They didn't do anything fundamentally different. And he's the one that came up with the iPad, the iPhone, the watch. I'm not sure what that's called. It's called the iWatch. That probably sounds about right. He's the one who came up with all these ideas. Now, somebody else could have come up with them, but he was the one that really pushed for them. And the iPad really changed the way music was done. And honestly, it changed workout clothing too, which is very interesting because a lot of them have pockets for an iPad or yeah, I think I'm thinking, or iPod, sorry, that does the music. Okay, so, and now it's kind of done to cell phones. And since his death, which means he's no longer there, they haven't really done anything innovative since. So, which is very interesting, which means Apple will, my guess is Apple will shrivel up and die if they don't come up with some innovative products eventually. They just go away. They become a dinosaur and they go away, especially since they're not a major player on the. They don't have the majority of the market share. I think they're around 30%. All it takes is somebody else to come along and take that away from them. It's possible. Okay. They use some of those products that I mentioned, like an iPod, would use an embedded system. Okay. They didn't use an off-the-shelf one, though. Okay. So one of the problems with these is in a regular computer, is that you have, if something goes wrong, and nowadays with the laptops and cell phones and things like that, it's not as common to have, you've maybe heard of it, the blue screen of death, right? The thing that makes your computer stop working, just effectively doesn't do anything anymore. I actually have this problem. There's a particular game that I play, and then sometimes during the game I'm going to Alt-Tab out of it. And if I do that at the wrong time, sometimes the game actually kind of gets weird and it won't go. It's something with the display, and so it won't render full screen any longer. And so it's just small. It's like a quarter of my screen, and I can, go into it and not, but I can't interact with it anymore once it's small. So when that happens, well, there's a user around to go ahead and just reboot the system. The user can know what to do, can figure it out. Well, hopefully, right? If nothing else, right, you can restart. On an embedded system, it's unlikely that you're going to be able to have that issue. Now, you might, right, with your coffee maker, but you might not if you've got, say there's a drone that's not remote controlled by a person, right? The drone actually can go out and take photos or look for something with its camera, and when it finds it, report its location. I don't know if the military is using these. It would be kind of silly if they didn't. And instead of talking about the big drones that the military uses, I'm talking about the little ones, right? They're not very big. They're about this big. And they can drop them out of a plane at fairly high altitudes that would be safer to fly over enemy territory, and they can drop these things, and they can drop 1,000 of them at a time, and they're not that expensive. And then they go and search for a tank, or they don't do anything to it, but they can search and find things. Or they can search for a specific kind of car or whatever it is, right? They can be programmed that way. And those are all independent, but they can also connect with each other as well, so that if they find it, they find whatever they're looking for, they can all start moving towards it, and then they can swarm around it. Now, they don't have any weapons on them, presumably, but they can communicate where the position is in the world, right, to tell people what's going on. And this could be helpful for even for finding, well, I don't know if you guys recall, there was a situation where there was a guy who was wanted. He was in some kind of a national park a while ago. I think it was last summer, maybe. Him and his girlfriend were YouTubers in like kind of like the van life thing, and she had been found, and they were looking for him. Or she had been found dead, and they were looking for him to question him. But he was out in some kind of a wilderness area, and so it would be difficult to scan that area. Well, you could use this group of drones to go out and do this. Would it be more effective than humans? I don't know, but you certainly can cover a lot of ground with a drone that you can't cover with a person walking through the woods. They're much faster. And because they're looking from the sky, they can see things potentially that a human would not. Especially if you get into some heavy underbrush, you can't see 5 feet, and you can't hear 10 feet. It's actually quite interesting with that. Anyways, back to embedded systems. So we can use the old system, right? We can use an old system. We can, because of the miniaturization, we can just use that design, so we don't have to design a new one, and they're just on the shelf. Oh, that's right, I've got that already. Anyways, what I wanted to do then is talk about what happens if there's a problem. Well, if there's a problem, it needs to be able to restart itself. And restart is maybe the wrong word for it. It needs to be able to rectify the situation. And one of the ways it does this is with something called a watchdog timer. Watchdog timer. And a watchdog timer it's a timer. Okay. It's a timer that goes on in the computer. And this timer will run until a certain amount of time. At the end of its time, so it's kind of like those old kitchen timers. I don't know if your parents or maybe your grandparents or maybe, who knows, right? You see that egg timer, right, that you twist, right? You twist it to the certain amount. Well, this watchdog timer, so it just ticks down. Every so many, milliseconds, it'll tick down one, and it'll just continue kicking down till it gets to 0. When it gets to 0, the alarm goes off, and then the system knows that something has gone wrong. That's how a watchdog timer works. And it does this with alerts and things like that. The advantage of using this, so here's an example. We could say, run a function, run function A. It does something. It doesn't matter what it does. Run function B. It does something. Or what we can do, but at the end, when function A completes, we can reset the watchdog timer back to its original setting, whatever that setting is. And so maybe it's the how long it takes for the system to work. Right? So let's take this drone example, right? It's going around looking for things. But if something has happened, right, a wind has come along and has pitched it, and it flips it upside down. And so it's flying weird. Well, you might have different systems for that. What would be different? Oh, a different system would be, right, it's going along, it's taking pictures or using video to try to find whatever it's looking for. It could be a lost dog. Then that's a really good use for it. So, right, it's looking for these things. It's using image recognition. But something happens, and the camera gets messed up. Not physically messed up, but the ability for the computer that's in there to look at the video that's coming in or analyze that video as something's gone wrong, and it recognizes everything as something it's not. And so what can happen is this watchdog timer can actually, because it times out. In this case, that's actually kind of a bad analogy because it doesn't time out. But when it times out, then it would kind of restart the analysis. But it would close it down, so whatever was wrong gets purged out of the system. And so that's the idea. Or if you have their function that gets into an infinite loop, that's a common problem that happens. And it gets into an infinite loop. I'm sure everyone has written an infinite loop by now. But you get into an infinite loop. Well, now that watchdog timer is allowed to stop that process and restart it. So that's very, very helpful. Okay. So that's pretty much the only difference between the old tech. If we take the old tech and move it forward, we probably have to add watchdog timers in there, just because it wouldn't be appropriate for the user to restart. Okay, there's some really interesting. Yeah. Okay, so let's look at. I'm going to look at in-depth 2, and then maybe talk about a third one, and then I think that's all we're going to have for tonight. Okay, so here's the styles, and this gets a little confusing. So if you're going to make your own programmable array logic. Okay, so let's kind of show how this works. So let me draw a line here. All right, so let's go x sub 0, x sub 1, and x sub 2. These are coming into the system, so we're going to look at how this is kind of wired. Suppose I could put a little bit darker here. It doesn't matter at this point. Okay. So let's say we have 3. We could have more than 3, but that's okay. 3 is enough to talk about. I'm just going to drag these way down here just to get plenty of room here for us. All right. Yeah, no, wait, I'm still doing it. Okay. Now, what we're going to do is we're going to put some AND accumulators here. Some AND gates. And so what we can do is we can run these AND gates out. This is exactly how this works, actually. And there'll be 6 of them that run out here. That connect to each of these lines coming down. But they're not necessarily turned on. You say, oh, okay, that doesn't make sense, does it? Well, yeah, it does. I'll explain it. Okay. So this is the real way this is wired. Another way we can show this because we're going to abstract it, because we don't really need to know all of those different wires, we can just do this. This AND gate here. And then, so, okay. Each one of these can be actuated or not actuated. So we can turn it on or we can turn it off. So we can make the connection there or not make the connection there. That's part of the programming of this. In fact, that's all of the programming of this. So what we can do is through switches, we can say, well, this one's on, and this one's on, and this one's on. So then here, when this comes out, we say this is X naught, X1, X2, X aught. So that this represents all three of these being on, which is great. So then what we're going to do, so we've got another one here, and another one here. What we're going to do is these are going to come down and they're going to go into an OR gate. Pretty pathetic looking OR gate, but it's an OR gate, just because I said so. And your instructor's never wrong, right? Except when he is. I think I've talked about my views on that. I understand that I will make mistakes just like everyone else. I'm a human. Humans are terribly fallible creatures. None of them are perfect. At least not anymore. There are certain religious beliefs that do believe that there have been people who have been perfect. But otherwise, I believe, I can't think of any religious belief that believes that people are perfect. And I don't know anyone who believes it either. There's a corollary there. That means you shouldn't believe 100% what anyone says. Or any organization says. Because organizations are made up of people. Take that for what it's worth. It also means we should be forgiving, though. It means we should say, okay, people make mistakes. They can learn, they can change, and get better. Okay, so and I'm not going to put in which one of these is stamped down here because it really doesn't matter that much. So now what happens for these outputs is they're going to they get collected through OR gates. And there could be more than two, right? There could be 4 or 5 or 6, however many. And this is how a programmable array logic works, is it's able to program on this big grid over here by flipping these switches and turning them on. And so then this will represent something different depending on what we do, right? So if we do those 3, but if we did these 3, we would get the negation of each of those. So that's just an idea to think about. And that's what a programmable logic array. No, programmable array logic. Okay, now. Now I'm going to confuse you. Maybe. Programmable logic array. Same words, different order. Just to confuse you. Oh, these are called pals, by the way. So we can use this circuitry to help us emulate other pieces of circuit, right? So maybe we don't have an adder, right? We might not have an adder for two 3-digit numbers in this case. Well, I could actually actuate this properly to make this into a 3-digit binary adder, which would be very useful. That'd be like a full adder, right? Because we have 3 inputs then. An A, a B, and a carry bit. So we could make this work for that. Okay, what's a programmable? Let me try to lasso the right amount of this, because it's a derivation of this. Got weird. Copy. Now undo. Copy, not paste. I'll go down here and paste it in. Okay, now. Okay, so here's the difference. So it looks like there's only one here, right, coming in, but there could be multiples. Hang on a second here. Let me draw this down. And this across here. So what we can do is we can say, oh, well, we want this one to go into this, so we're going to go ahead and stamp this down. And then stamp this down here, and maybe this down here. So what it's going to do is it's going to take the result from this one and the result from this one and pass it through that OR gate. The same thing over here, only this time it only has one option. So it's just going to go ahead and shoot on through. Well, OR gates get a little, you have to do some funny defining what happens if they, not funny, right? An OR gate that has only one input into it will trigger. And an AND gate that only has one input into it will trigger. It becomes just a pass-through, so it just automatically works. Or maybe an AND gate requires that you need two, not necessarily you need two in order to get a true value, so that the second thing that's coming in, you think that, that you can just think that if there's an absence of that other one, then that becomes a zero or a false. So what this does, right, is allows us to program on this side as well, because in a PAL, oh, this is a PLA. I didn't pick it. That's what it's called. So what we can do, instead of having this all hard-coded, we have the switches in here that help us figure out which of these outputs then are the correct answer, or what we're looking for. And so it's just a matter of toggling our switches to get our generic gates into a specific gate that we want. So we can create the truth table for these two outputs that are coming out of our system. That's it. All that is. Pretty straightforward. So then the next one, the third one, that I'm not going to talk about as in depth, but it is the field So when I hear this, I think field trials. And field trials would be when it goes out into the world and gets to get tried. Well, so this means in the field, right? Not where you're working on it, but somewhere's out there, someone else gets to program this. And this, believe it or not, is FPGA. There's an acronym. Computer scientists are fond of our acronyms of things. So what is it? Not an acronym. NAA. So actually, there's, what is it? GNU. So here's one. GNU. So it's both self-referential. It's self-referential. This is what it. So it stands for GNU is not Unix. That's the meaning of it. That's what the acronym is for. GNU is not Unix. So anyways, that's our GNU. That's our thing about that. Okay. Don't need to talk about that more. All right, so I think for this one, the best thing I can do is let me get this right off screen here. I found this really neat website that will show it to us. I don't really care about those. It's a type of integrated circuit that enables the development of custom logic for valid prototyping and final system design. So this is one that allows us to kind of change things as we go. But it's custom, right? Their inherent flexibility that allows it to be programmed and reprogrammed via software loaded. Okay, so let's look. Let's see. This is big grid. But when we zoom in on the grid, we have a programmable logic unit. We don't know what that is, right? It could be any kind of a logic unit you can think of it, or it's a specific thing that's going to do it's a specific circuit that does a specific thing for us. Then these are all programmable interchanges. So what I can do is I can either turn them on or turn them off, or they can be more sophisticated than that. So it allows for data to maybe travel down through these, or navigate different directions. And so it allows the logic to move around in their system more programmatically, right? So we can set switches and logic gates. We can't do it inside the logic units, but we can do the other ones, the programmable interconnections. And actually this one right here has a special name as well. Does it talk about it? No. So one of the advantages of the programmable gate array is that what I can do is I can use something like this to kind of do a proof of concept. And then maybe I can start working on something more difficult. So I could use this to prove that I can solve the problem, or prove that I can program this thing correctly. So this is very generic things. Okay. Oh, a couple more things here. So we can then go to custom chips. So these aren't necessarily, those weren't custom chips. Those are all programmable chips. So now we go to custom chips. Right? I don't even know what to do for that one. I just leave it there. Yes. So custom chips. because you could literally design your own. The problem with designing your own is actually quite expensive, and the cost is the human cost, the cost of time that it takes to figure out how everything is going to work, which is why things like the field programmable gate array is so useful, because it allows us to program something. We have a chip already that we can just program. A customized chip is a chip that we're going to build from scratch. Okay. So what I want to do is I want to show you this Gajki-Kohn Y chart. This takes a little bit of explaining. These concentric circles are the same level of abstraction. So when I look here and I say an algorithm relies on processors, relies on something called a floor plan. Register transistors rely on it. They work like ALU and RAM, and they are laid out in a module layout. So then same thing here, we've got transfer protocols, transistor layout. So this is behavior. So if we look, none of this is how things are built. It's just how they abstractly, we can kind of abstractly think about them, or how they work. And this is all how they're built, structure, right? And then this is actually how they're configured together. And this is the physical domain. No, this is how they're put together, the physical domain. The structural domain is actually what they are, so that like the transistors or the gates, flip-flops. And so you can actually use this to help you kind of understand like what layer to use or how to work through creating your own chips here. And that's the idea here. And this is called, Gajki-Kohn Y chart. Let me go back here. Gajki-Kohn Y chart. Now the book leaves off Kohn, but I think more recently we don't. So we'll go with the newer version of this. All right, it's a model that captures the considerations in designed semiconductor devices. The three domains are on radial axes. Each of the domains can be divided into levels of abstraction using concentric rings. On the upper or outer level, we consider the architecture of the chip. At the lower levels, we successfully refine the design into finer detailed implementation. So that's that, right? So we just get lower and smaller and things like that. Okay, so now let me give you two more things, and then we'll probably be done. I think there's a lot of stuff in here. I mean, it talks about like what languages you're going to use and blah blah blah, all that other stuff. But you know what? When it comes time, you're going to figure it out. Most of these chips are designed in some kind of C or C-like language, because sometimes people will make their own languages to go on them. And there's a ton of different design decisions. I don't want to bog you down with it. I think it's kind of, it's a bit much. So we're not going to worry too much about some of the minutia there. And so we'll see how this ends up working out for us. Okay, so yeah. I put up a new assignment that's due on Friday, and then I put up a project. And I want that project to be submitted in text form. So .txt. So, and I think I put that on there. I hope I did. So Now that one is due the day after Thanksgiving. So it's an interesting one. So it's kind of a mini break for us, right? So we don't have class on Thursday or Friday of that week. So that's great. However, I'm making it due on that date. You're certainly welcome to do it before you go on Thanksgiving break. So I'm putting it as the due date of that time. I could, if people don't like that as being the due date, think of it in your head, or I can change the date if you really want me to the Wednesday before Thanksgiving. Although I think it's just as easy to give you guys 2 extra days and not worry about it. So, and that will be, I'll look into seeing about getting a rubric written up for that one. And that the rubric will be basically, does it do this, does it do this, does it do this? And if it does those things, then you'll get those points. And that's how that'll work. Okay. And for programs, which I didn't talk about before, I do have a certain percentage of the grade that is about readability. And I know that's kind of strange for a assembly language program, but if things aren't formatted nicely so that I can read them easily, for those of you who are wondering, I will not be using Notepad. I will be using Notepad++ to evaluate them and to look at them. Well, actually, I'll probably be using Marie. So, .js. I'll use this. I will just, agree to end the tour, yeah. So I will just simply go here. I'll go in. I'll upload your work, and I'll find it, and I'll upload it, and then that's how I'll look at it, and then I'll do step by step through it and see how everything works. I would ask that you put it in code like this, and not in code like this, right? This is all written in hex code, so don't do this. I simply won't. I mean, I might be able to grade part of it, but I can't. I'm not going to dig into all of it if I can't read your logic. Okay, so that's all there. I'm going to try to make a rubric. Let me make a note of that here. Yeah, and then I'll come up with another one that'll be due right at the end of the semester. So, all right, that's all I've got for today. I know it's kind of short, but embedded systems are pretty straightforward. It's for the most part, they're so custom that it's really hard to kind of go over too much about how they work because each one is different and interesting. So, all right, that's all I've got. I will talk to you all in a couple more days. All right, bye-bye.